Welcome back, everyone. It's my pleasure to introduce the next speaker. As you know, we don't do very long introductions, but I feel like I have to say something because we are colleagues at the University of Cambridge with Ryan, but he also just defended his PhD at Johns Hopkins University, hence the ambiguity, if you like. So today, I'm very pleased that he's here to give us a talk on probabilistic topology, generating language from scratch. And over to you.
Yeah, hi. So I'll give you some comments about what a thesis defense looks like. This is 2/3. Can you guys hear me? I guess this is 2/3 of a thesis defense. And I still won't be a doctor until December because my advisor wants a massive number of corrections. And that is despite that one of these papers won a best paper at ACL, he still wants it to be better. So you know what, it's a very hard thing to get a PhD, so you should all be very proud of yourselves when you graduate. Anyway, I'm going to talk about probabilistic typology and generating languages from scratch. So this is a talk I've been working on for a couple years. It's composed of two papers mostly. One was at ACL in 2017, and the other was at NACL last year. And the third part of my thesis will be at EMNLP this year. But the slides aren't quite there yet. So I'd like to start off with a bit of a linguistic overview, sort of so you can understand where I'm coming from with this line of research, because it tends to be a bit different than what you typically see at ACL conference venues. So I typically start this, this is annoying. I typically start this talk off with a game. So the game I want you to play is to come up with a language, a brand new language. And what I'd like to happen is that I want that this language sounds natural. So, you know, if someone spoke to you in this made-up language, you might actually believe that it's a human production. In other words, I don't really want it to look like computer code. So let's take an example of an actual constructed language. So how about Dothraki? So for those who don't know, Dothraki is a made-up language that was featured on HBO's TV series Game of Thrones that recently ended. And importantly, this language is fully fledged. It has a full lexicon and grammar. So here is Khal Drogo, a very popular character on the show, wishing you a happy birthday. Anhajelek Ashkoya Veshnieran. It's actually the Dothraki for happy birthday. So the question that I'm really asking in this, you know, the larger question, this is the beginning of a talk where, you know, you express your aspirations, which are research code for things you haven't achieved yet. But anyway, the question I'm interested in, and this is something I've been interested in for quite some time since I was undergrad, is what makes it sound like a natural language? So why, when you watch Game of Thrones, why do you actually believe that's a human language? Why does it not strike you like they're speaking computer code? So the reason is it was invented by a linguist. Specifically, Dothraki was invented by the linguist David Peterson. And David Peterson has used linguistic knowledge to come up with about tens of different languages for different TV shows and movies in Hollywood. He's even written a book about it, which, yeah. I guess I'm being filmed. Anyway, and what's interesting about David Peterson is while most linguists analyze language, what David Peterson does is he generates languages. And he uses a specific branch of linguistics known as typology to construct new languages. And what he ends up doing is he sort of takes together different bits and pieces from existing languages and tries to come up with something that will sound natural. So a fundamental question in this work, or the fundamental question, is wouldn't it be fun to build a David_Peterson.py? That is, I'd like some sort of Python program, much like the ones you are coming up with today, from which I could sample a new language. And what I'd like to have happen is that every sample of this language really sounds human. So arguably, if we knew what this program looked like, or we knew what this distribution was that this program is sampling from, we'd have something that sort of looks like Chomsky universal grammar, if you know what that is. That is sort of this idea that language comes from some prior, and all human languages are somewhat the same. That's a very Bayesian interpretation of universal grammar, for which I often take a lot of flack for. But anyway, we don't really know that much about universal grammar, but for now, we assume that David's brain has a good approximation. So at this point, I want to emphasize that this sort of problem of generating a new language, it's fun to talk about, but it's also an incredibly difficult problem. So natural language processing as a field these days is focusing on many different text generation tasks. For instance, machine translation, where you take a source language and generate a new language, or some dialogue system. And what I'm asking you to do is not just generate text from an existing language where you have, I guess, billions of words in the case of English. I'm asking you to generate text from a brand new language that doesn't exist. Okay. So it may not be entirely obvious to you, but designing a new language is incredibly complicated. So just give you sort of the range of possibilities that sort of exist and how the things you have to specify when you want to come up with a new language. Let's first start with syntax. So a basic notion in syntax is that of a word order. And this is canonical word order. So in English, we typically put the subject before the verb, and then that's followed by the object, as in David invented 13 languages. So this is called SVO word order, whereas Yoda would say 13 languages David invented. That is object, subject, verb word order. Now, if you looked at the distribution over word orders in the world's languages, you might expect that they're somewhat uniform, that any of these 6 possible word orders is equally likely. But that's in fact not what you find. What we find is that SOV and SVO account for the vast majority of the world's languages. So Khal Drogo's word order is actually quite common. It's the same as mine as a native English speaker. But Yoda's word order is really rare. In fact, people thought it didn't exist until they discovered Warao, which is spoken in the Amazon. So clearly, what we'd like to do is when we sample a new language, for it to sound natural, we'd like this distribution, we'd like the distribution we sample from to reflect these sort of properties. Okay. But it doesn't just stop with syntax. We also would need to choose a morphology. So morphology is one of the more interesting bits of language because it's one of the few things where you get a choice. A lot of languages don't have morphology. Every language has a word order. Every language has a sound system, except for the sign languages, of course. But we actually have to choose. Do you want a morphology? Chinese is an example of a language which is said to not have an inflectional morphology. So once you choose, maybe you do want an inflectional morphology, you could choose one that's relatively impoverished, like English. English makes 4 distinctions, typically in a verb, with run, runs, running, and ran. Whereas Spanish marked close to 100. And in fact, there are some languages where an individual word form, an individual lemma, will have over 10,000 possible inflections. An example of that is Archie, which is spoken in the Caucasus. And additionally, we also need to specify a phonology. So we'd like to speak this language, we have to choose the sounds. So we have to ask basic questions like, does your language have a velar fricative? So in this case, you'd have 2 choices. You could have a voiced r, unvoiced r. And if you're a fan of Game of Thrones, you may notice that Dothraki has both. That's why it sounds so guttural. Also, we have to deal with contextual phonology. So does your language allow word final voiced obstruents? So in English, we can end words in a G sound. That is, you can say bug and bugs. But this is actually not possible in German. There are no German words that end in a G sound. They may look like they end in a G sound, like Zug, but they're actually pronounced with a K, as in Zug. So you also have to choose these sorts of rules that will determine how your language is pronounced. Okay. So after sort of all that highfalutin talk, there's actually a fundamental scientific question behind making a new language, which is the question I'm most interested in as a scientist. And that question is, why are some types of languages more common than others? So this is arguably the purpose of linguistics in my mind, because linguists don't just seek to explain, don't just seek to describe languages, they seek to explain why those languages are the way they are. And I found when introducing these concepts to computer scientists, talking about it in terms of a generation game is often more helpful to sort of explain the linguistic concepts. And there is a connection here, which I often talk about, between generative grammar and generative modeling. Have you guys heard of generative modeling? Which idea is that we want something that, generates a language. Generative grammar wants to specify a set of all possible grammatical sentences. You could also think about that as a distribution if you'd like. But anyway, so moving on. Traditionally, linguistic typologists have worked on what I like to call possible typology. This is not their term. But possible typology works like this. So imagine we have a graph like this. Now on this graph, every blue point is a language. Now I've taken this from the universal dependencies corpus. Now the x-axis is how often the direct object appears to the right of the verb, and the y-axis is how often the adverb appears to the right of the verb. Now what a possible typologist might want to do with languages is they might want to draw a box right around that. They like to say, okay, see that box right there? That box is the space of all human languages. But of course, a typologist would also note that this sort of misses the generalization. So the generalization here is that these two quantities in natural language tend to be correlated. So the fundamental idea that we had proposed in this motion to move the study of typology from the possible to the probable is to place a distribution over the space of human languages. So once we've done this, we've sort of started talking about linguistics in slightly different terms because we get to use tools from NLP and machine learning to answer some interesting questions. So when we talk about building a generative model over languages, we ask, what's the generative probability model that gave rise to those languages? Importantly, what scientific ideas are in that probability model? And finally, we get a nice evaluation metric, which is, does it predict held-out language as well? So this is an important one, and I'll talk about this a bit later, because I often have, I guess, issues with the way some linguists evaluate their work. Because in machine learning, I'm sure as you guys all know, it's very, very important to have a separate train, dev, and test plot. This is not something that linguistics as a science often does. They often look at all of their data. They come up with a theory that fits all of the data, and then they publish it. It's true. But anyway, so the linguistic model, I should be charitable to the linguists. The linguistics model as a science is that I have all of my data, and my model has to fit the data perfectly, so I'm going to fit it. And then it's up to someone else to actually come and show that it doesn't properly generalize. Find a new language that breaks it. So it's sort of like you run this train dev test split over multiple papers. At least that's how I've come to think of their publication model. Anyway, this first paper focuses specifically on vowel system typology. So vowel systems are something that is near and dear to my heart, as I was trained as a phonologist far before I became a computer scientist. So I'm going to get into sort of like the nitty-gritty of phonology and phonetics to the extent that I have time for. So it's a typological universal that all spoken languages have vowels. So a universal is something that's true for all languages. That is, there are no spoken languages that don't have vowels. It's actually quite an interesting question to try and define the word vowel, which maybe I hadn't thought about before I had taken linguistics classes, but it's a fun exercise. See if you could do it in your own language, and maybe prove to yourself that's a rigorous definition. But anyway, the question in this paper is what makes a good vowel system? So what I'm talking about is trying to figure out why English is said to have the vowels A, E, I, O, and U, and I've just talked about the orthographic symbols there and all the different sounds, and why that's a relatively common set of sounds. And you might think this is a very, very simple question. If we can't estimate a model for just picking vowel types, how could we possibly handle the rest of language? So I talked to you about generating new text, new syntax systems, new morphologies. But now for the rest of this talk, we have about 45 minutes. We'll say we have 45 minutes. I'm going to talk to you about vowel systems. And because this problem is so simple, I think it's the perfect point for sort of an investigation into the study of probabilistic typology. Okay, so now I'd like to talk about phonetics for a bit. So at this point, I'd like to compress an entire field of study into one PowerPoint slide. Are there any linguists in the room? Oh no. So tell me if I do it wrong. Okay. I've had varying success with this slide. Anyway, okay, here it goes. So, it may not come as a surprise to you, but the sound quality of a vowel can be measured. So what you should think of is vowels as vectors in acoustic space. For instance, there's a canonical drawing where we used to represent a language's vowel system. It's this trapezoid over there, and every vowel is represented by a point in 2 space. Now, the numbers there are the first 2 formants, and the formants are the spectral peaks of the vowel. So that diagram up there is called a spectrogram, and that is what happens when you have someone's vowel, when you record someone saying a vowel, like that's E, U, A. You run a short-time Fourier transform, and you find the peaks of it. So those are the really, really dark points, and those are called the formants. So what I've started to ask my computer scientists to think of, or to start to ask them to consider vowels as word embeddings, because that's something you're comfortable with. That is, when you think of a vowel, think of it as some embedding in the plane, and for this reason, some vowels are closer than others, and they're more similar along different dimensions. For instance, this shows the canonical 2 dimensions, which is that there's a height dimension that's up and down, and there's a front versus back, that's a left to right. So E over there is a high front vowel, but A over there is a low back vowel. So these are just like word embeddings. Right. So if we look at some example vowel systems in the wild, now these are all taken from Wikipedia, so you could take your favorite language, and you could go to that language's Wikipedia page, and you could find such a trapezoid. So here I've taken a bias sample of 6 languages. So these are the different symbols. What you might notice is that there's immediate similarities between the languages. Like all of the languages have that symbol E. And also, they tend to be sort of spread out. So it's not the case that we observe vowel systems that look like this. That is, they contain mostly infrequent vowels. Now, how many of you guys are familiar with IPA? Many? So I have IPA is the International Phonetic Alphabet. It's the symbols that I'm using to write the vowels there. And when we talk about frequency, there's actually a very cute life hack, which is that if you look at the symbol and you say, I don't really recognize it, it means it's very rare. So the common vowels have more commonly used Roman symbols from the Roman alphabet, like the Y. So that symbol, that system has mostly uncommon vowels. It has what is effectively a gamma. I don't even know how to pronounce that. Anyway, so we rarely observe vowel systems that mostly contain infrequent vowels, and we also don't tend to observe vowel systems that look like this. So this sort of horizontal vowel system where the vowels are not spread out is never attested. So of the thousands of languages we know in the world, not a single one looks like that. Okay. So the goal of the linguists who look into this is to try and explain these facts. We'd like a theory of why the vowel systems of language tend to look this way. So this has led to 2 sort of proposed undergirding principles of vowel systems, and I'm going to discuss them. And then eventually, to sort of foreshadow, I'm going to discuss how you can take these sort of softer linguistic principles and incorporate them into a generative model. Okay, so the first principle of vowel systems is called focalization. And this is the idea that some vowels are phonetically better than others. That is, not all vowels are created equal. So here I have a data set of about 300 languages, and this plots the frequency of the different IPA symbols. So that vowel that I showed you up in the corner that almost every system had is actually attested in 90% of the world's languages. But some of these rarer symbols, like over there is that one over there is the German umlauted O is Ö. That's a very, very rare sound. Right, so ideally a good vowel system would have some of these more focalized vowels. Now focalization, for my linguist friends, because they always get upset when I don't mention this, is actually a very well specified theory due to Kenneth Stevens, and it has to do with to the best of my understanding, it has to do with how close the different formant values are together. But in this sense, I'm using focalization almost in a term of markedness, that these are less marked vowels, or just better vowels. Okay. So the second principle that goes into a good vowel system is known as dispersion. So this says that good vowel systems are spread out in the space. So that is, if we have the vowel system here, this is English, the received pronunciation in the UK, we might say that if we budge that vowel up there, that would be a comparatively worse vowel system. Okay. So now I'd like to talk about the first set of, This one? Let's go back where we were. So here, it's the first two formants, right? So the x is going to be the first formant, and the y is going to be the second formant, I believe. Yes, so the formants are, so if you look at the spectrogram, can you guys the spectrogram over there, you see the different arrows. Those show the frequencies of the different formant values of the vowels. So it's widely believed that the formant values are almost enough in certain cases to distinguish between vowels. So this is what happens is when you take a measurement of a vowel, like in a software program like Prot, this is the sort of thing you might want to extract as a signature of the vowel. So when I say think about this as word embeddings, I mean when you observe a word type, like, I don't know, a word like dog, and then you have its embedding, which sort of tells you something about the meaning. When you extract this sort of vector, it tells you something about the quality of the vowel. Any other questions? Comments? Okay, cool. Okay, so now I'm going to move on to the first set of probabilistic models that I worked on in my PhD thesis. So this was to come up with distributions over phonemes. Okay. So the larger goal of the research agenda as a whole is to come up with a generative probabilistic typology. So what I'd like to construct here is a trainable generative probability model over all of the world's languages, and I'm going to start with vowel systems. So to come up with a distribution over phonemes, the basic setup is going to look like this. We're going to have a base set of vowels. I'm going to represent this as cal v, so this is, you can think of as the set of IPA symbols. And then the goal is to come up with the distributions over subsets of this base set. For instance, we'd like some probability distribution over all subsets. And we're going to estimate the parameters of this model by training on hundreds of languages to get sort of a sense for what vowel systems look like. And then, and crucially, we're going to evaluate it on held out languages. So the generative model is going to be pretty simple. We're going to define a score function, and the score function is going to take a vowel system as an input, and it's going to define the goodness of the vowel system. And then we're going to state that the probability measure is proportional to the goodness of that vowel system. So the key scientific questions in this are, how do we define a score function such that it encodes different notions of the different notions of focalization and dispersion? And again, this is a question in linguistics. That is, I'd like to build a generative probability model that I view as a theory of language, but I'd like to approach this problem with tools from NLP and machine learning. Okay. So the first paper we had in 2017 introduced 3 different probability models of vowel systems. The probability models differ in how they quantify focalization dispersion, and primarily they differ in how they quantify dispersion. So the first model, which is sort of the baseline, can only score interactions, cannot score any interactions. It scores 1 vowel at a time. The second one will score 2 vowels at a time, and the third one will score all the vowels together. And this is where we get into some fun, I guess, machine learning, because when you talk about scoring pairs of vowels or multiple vowels together, you're talking about a structure prediction problem. Actually, to be very clear, just because you guys have had lectures in structure prediction here, I guess, right? Or you will have had. But to be very clear, just because why I want to go over why this specifically is a structure prediction problem, is because when we a structure prediction problem, in my view of the world, is basically whenever you have a classification model and you have an exponentially large number of classes. So we're trying to place a distribution over the space of all subsets of a base set. And there are 2 to the n number of those subsets. Okay, so the first model of vowel systems that we introduced is called a Bernoulli point process. So that is I guess, a statistical name for the model, and it's quite simple. You can think of it as independent weighted coin flips, but these are not IAD. So this means that the ith vowel is included in our sample with probability p sub I. So this gives us a very simple score function that looks like this. And what you might notice about this score function is that it's actually self-normalized. So this score function is the probability. And crucially, there's going to be no interaction between the vowels. So this model can only model focalization, no dispersion. And for that reason, it's a very interesting baseline, because linguists sometimes quibble over the relative importance of focalization dispersion, and this is a purely focalization model. However, samples from this model will look like this at times because there will be no dispersion. So we might want to do a bit better. So sort of the technical meat of this work comes in the idea of how can we actually come up with a model that will allow us to model these dispersive processes, or these repulsive processes that make vowel systems look the way they do. So to do this, we rely on the notion of the geometry of a vowel space. So this goes back to the idea that I told you guys to think of vowels as word embeddings. So if we think of these as vowels as different embeddings, what we want is the simple idea that similar vowels, that is similar, close to each other in the space, tend not to co-appear in the same system. So this leads to a very natural second model, which generalizes the Bernoulli point process. And this is called a Boltzmann machine or a Markov point process. So we multiply together, first of all, a series of unary factors, and these encourage high focalization. So this model, as it stands here, even though I've written it in terms of different notation, I've used phi here as a non-negative potential function. This is actually equivalent to the Bernoulli point process. However, then we multiply in a series of binary factors that encourage high dispersion. That is, we encourage the vowels to be pushed apart. And specifically, we've chosen to define this as the negative inverse of the Euclidean distance, which is loosely inspired by Coulomb's law. So this will give us the repulsive processes that we want. However, a natural question might be, and is, once we've modeled pairs of interactions, can we do better? The final model that I looked at is called a determinantal point process. So the determinantal point process is a very elegant stochastic point process that's based on sort of some notions from linear algebra that I'll review. So just a terminological note, how many of you know what a point process is? It sounds very, very fancy when you say a stochastic point process, but all that means is a distribution over subsets of a set. But yeah, okay. So the way to think of a determinantal point process is like this. So if we go back to this notion of vowels as vectors, what a determinantal point process says is that we'd like to sample a collection of vowels that correspond to the volume of the parallelepiped that are created, that you get from these two vectors. Specifically, you define the score of a vowel system as the squared volume of that parallelepiped. So intuitively what this does is it means that the model should prefer longer vectors. That is, we get quality is encoded as length. And it should also prefer sets of more orthogonal vectors. So diversity and dispersion are encoded as how orthogonal they are. So to compute this, what we do is we create what's called a Graham matrix, where every entry of that matrix is the dot product between two vowel vectors. And then, as you may remember from linear algebra, the squared volume of a parallelepiped is just the determinant. So what we do is to get the score of, say, this vowel system, we take the submatrix, that is what that L sub v is, and then we take the determinant of this matrix. And these last two models will give us the ability to sample well-dispersed systems. So to talk a bit about the complexity of inference, and specifically by inference, I mean the computational problem of summing over all vowel system scores. So there are exponentially many summands in there, so this is a hard problem. So the first model, the Bernoulli point process, allows us to perform inference in linear time, and that's because there is no interaction between them. We can just look at each vowel independently. The second model, the Markov point process, is actually sharp p hard. It's sharp p hard to compute the normalizing constant. And that's a general result for all Markov random fields. However, what makes a determinant point process so interesting is despite the fact that we sum over an exponentially large number of vowel systems, we actually have the result that we can do this in cubic time, and it allows interactions from all these different vowels to contribute. So the reason for these different complexities is that the first model, as I said, doesn't allow interactions, but the determinant point process is quite elegant because it only allows negative interactions between vowels, which is actually what you might think you'd want in a vowel system, because dispersion means you push the vowels apart. So this is actually a tractable model. So in addition to simply defining distributions over here, over vowel systems, we'd also like to tune a similarity function. That is, before, when I said we talked about how similar vowels are, we might just not want to look at, say, a dot product, but tune a function that's going to tell us how similar two vowels are. So this is loosely inspired by the fact that the human ear performs a nonlinear transformation of acoustic space into perceptual space. So what we end up doing is we learn a universal similarity function that allow us to help predict which vowels are attested. So roughly, we want to learn a function that looks like this. So one such learned function is this here. So what we've done here is we've mapped an infinite number of vowels, that's all those blue points, into some sort of, through a funhouse mirror to get the red points. And we have the original vowels here in blue and the transformed vowels here in red, and this allows us to move the similarity between vowels in order to help prediction. So the way we do this is with neural vowel embeddings. So what we do is we feed in the first two formants, and then we run them through a neural network. So in linear algebra, that looks like this. However, this net model might actually be far too powerful for our purposes, because neural networks are capable of learning arbitrary transpositions. So in our interpretal model, that is the model we use to generate that plot, we actually rely on a certain type of multilayer perceptron, specifically one that's a diffeomorphism. So that word is just a very scary math word that just means that any invertible function where both it and its inverse are smooth. So this will prevent it from warping the space so much. So what this means in terms of defining our neural network is that we have to have the projection matrix be the same dimensionality as the input, and we have to have smooth and invertible activation functions, and we have to have matrices that are a full rank. So pictorially, what this means is that we have to go down to two hidden layers and choose our activation functions judiciously, but we can stack the nodes arbitrarily deep. So now in the experimental portion, we've compared these three different models. So the goal here is to evaluate on held out languages. That is, we want to see how well our models are at predicting new vowel systems. So the first task is cross entropy. That is, we want to measure how surprised the models were, and this is measured in gnats. And the second task is a closed task, where we hold out a vowel and ask how well the model, yeah? Gnats? Right. So in information theory, we often have the concept of bits. Do you know that? So bits is based when you have log base 2. A nat is what happened when you have log base e, which is log base e, like natural. Ah, okay. It's just, sometimes people forget to divide by log 2, and it's just easier if it's in nats, then I don't know I didn't make a mistake. And the final task, so actually just go back to it. It's actually because if you know the logarithm formula, right, to change base, it's actually just a constant, right? more or less. And the final is a map decode, where we take the one best decodes out of our system and ask if they look like real systems. So that's more of a qualitative evaluation. Okay. So now I'd like to move on to the next section. So how much time do I have left? 15 minutes, good. Okay. Now I'd like to move to the next section. So in the second paper, so the second, I guess the third chapter of my thesis was largely about how to generate well-dispersed phones. So the thing about vowel systems is that before, I talked to you a bit about phonetics, and then I defined several distributions over phonemes. Those are discrete units. But what I'd like to move on to do is define distributions over actual phonetic quantities. That is, what I'd like to do is come up with a generative model over, over these pairs of formant values that we extracted before. So in contrast before, we need to construct actually a much more interesting distribution. So what we'd like to have is a distribution over all possible subsets of pairs of formants values, and those live in R2. So again, we're going to train this on hundreds of languages and evaluate it on held out languages. So visually, where before we generated symbols, now we have to generate actual real values. So the computational problem here is that sampling from a distribution over a continuous subset is incredibly hard. Before, we had a series of tractable algorithms for these discrete cases, but in the continuous case, it's much, much harder. So the key idea that we first introduced was, as opposed to generating directly defining a point process over continuous values, we actually defined a point process over distributions, in this case over Gaussians, and then from each Gaussian, we then sampled a prototype. We then sampled an actual pronunciation. So what this means is that when we want to select, we've sort of reduced the problem of sampling from a continuous base set to one of sampling from a discrete base set where the elements of that discrete base set are Gaussians. We then select a subset of those Gaussians. So this is something we can do tractably. And then we sample from each of those Gaussians. So there are two computational problems in this model, which is what we spent most of the time working out. The first is, how does each language select the subset of Gaussian phones from which we want to select a pronunciation? The solution is we'd like them to be both dispersed and focalized as before. So when I talked to you about similarity between vowels, I said they were kind of like word embeddings because we could naturally talk about them in Euclidean space. But the question here is a bit more complicated. So what does it mean for two distributions to be similar? So it turns out that there is a relatively natural notion of this. So we can look at how much overlap there are between the Gaussians. So here, we might say we have two similar Gaussians, whereas here, we have two diverse Gaussians. So a natural measure of this is called the probability kernel, which is sort of exactly what you'd expect. It's an integral that sort of measures how much overlap there are between these two things. And this was introduced by Jabbar et al. In 2004. And for bivariate Gaussians, we actually have a nice closed form. So we have a very simple expression that tells us how similar these underlying phones are. So just like before in this generalization of the previous models, we're going to compute a pairwise similarity matrix. However, as opposed to having each element of the similarity matrix be a dot product, we're going to have each element be the probability kernel. So this allows us to come up with a determinantal point process as we did before, but we're going to score sets of Gaussians. So the second problem we encountered when we wanted to set up this model over continuous pronunciations is how do we match sort of the observed pronunciations to the individual phones that we observe. So the answer to this was to treat the alignment between the Gaussians and the observed phones as a latent variable. So concretely, what we might observe in a vowel system is a series of pronunciations like this. So these would be 3 pronunciations in R2. We know that they could have been from a larger set. However, we only have a finite set of Gaussians, which we need to infer an alignment between which Gaussian generated each point that we observe. So this would actually be very straightforward to perform estimation in this model if we observe the alignment. In this case, that computation would be easy. The probability of a vowel system is simply the probability that each Gaussian that is known generated the individual phones times the probability of that collection of Gaussians. However, we don't actually know which Gaussian generated each individual point because it's a latent variable. So what we have to do is sum over all possible alignments between the Gaussians, those underlying Gaussian phones, and the observed pronunciation. So this is actually a very classic problem in graph theory. It's called the bipartite matching problem. So there are an exponential number of alignments. It's another classic sharp P hard problem, but we employ approximate inference with Gibbs sampling. So there is actually, this is an interesting case because the summation problem is sharp P hard, but there's actually a tractable algorithm known as the Hungarian algorithm for the maximum, the case of finding the maximum weight bipartite matching. So the next question that we ask is sort of how do we actually learn this Gaussian, and do we actually believe that a Gaussian is a good representation of the space of possible vowels? So like before, we're going to sort of warp the space using a neural network. So in this model, we're going to use a neural Gaussian, just like before how we tune the similarity function. And what this looks like is a very simple generative model. So Gaussians are often convenient because they're easy to work with and they offer closed form solutions, but they are unimodal and probably can't represent all possible distributions we like to find. But if we have something like a neural Gaussian, that is when we take the output of a Gaussian and run it through a neural network, we still have a closed form distribution, but we can represent a larger space of distributions. So what this looks like in terms of sampling is we first sample from a Gaussian, and then we run that sample through a neural network. So more formally, so some of you may be familiar with this trick in terms of variational inference. But what you end up doing is you simply apply the change of variable formula, which is sort of basic probability, where you get a nice closed form expression for a neural Gaussian by taking the original Gaussian, applying the inverse of the neural network, which requires that we have the same constraint before, that it's a diffeomorphism, and then we multiply by the Jacobian determinant. Okay. So this gives us the complete model of actual vowel formants. So the first step is, again, where we sample a diverse set of Gaussians from a determinantal point process. The second step is where we sample formants from each Gaussian. And then the third step is where we compute a nonlinear transformation of those formants. And this gives us a generative process by which we can actually create vowel systems. So to look at the results of this system, or sorry, the Foreman system, what we learned is actually that these models tend to do very similarly. That is, we have the neural determinantal point process. We ablated, we took out the neural network in the second box, and the third is the Bernoulli point process. And the numbers at the bottom are how many prototypes we had. And what we actually learned was that our induced phonemic categories are much better than a linguistics baseline, which is where we took the phonemes that a linguist would prescribe. And what we interpreted this to be is that the IPA symbols aren't as cross-linguistically compatible as we would like them to be. So the high-level ideas from both the papers were most that modeling dispersion in this way helps, and this is and neuralizing the Gaussian helps us model vowel systems better. So the conclusion is that you can sort of use NLP tools to do science and not just engineering. And we ended up building a David_Peterson_vowels, but you can build your own David Peterson too. And I do end with this quote, which I found by Christopher Manning in a recent computational linguistics article, where he argues that it would be good to sort of return some emphasis within NLP to the cognitive and scientific investigation of language, rather than almost exclusively using an engineering model of research, which is sort of what our community does these days. So, thanks.
Have time for a few questions.
Human language, is this something that has been actually proved, and how would you ever even prove it? I mean, how would you set up such an experiment? Because I guess it depends on how you sample the negative, the non-existing language, and what you would find out.
That's a very complicated question. I don't think any study has been done that I know of. So the question is, are you asking like, you could imagine a version of Game of Thrones where people were told that Dothraki was actually Finnish, and how many of the audience would have actually believed it? Is that basically the question? You're asking if people can distinguish human languages from from artificial ones?
Yes, you say that's a language that sounds like human. How do you formalize that notion?
I mean, I don't think there's ever been a study, but I mean, it is true that when people watch media with conlangs, they tend to believe they're human. Like, I don't know of anyone who looked at Game of Thrones and thought, well, that language is clearly some made-up thing. They were sort of impressed, yeah, it could be a language.
But I'm curious about the example where people say, oh, no, this doesn't really sound like a human language.
Right. So I think my example was a programming language. So I think that's
but that's very, very distant, right? So
yes,
maybe you can sample a language with one of your bad models and the baselines, and then you ask a human, does it sound like a real language? And then they should say no. That would be really interesting.
That'd be interesting. I mean, I've mostly worked on sampling vowel systems, so I have a way to go before you get a full language.
Well, can you do that with a vowel system? Can you ask a human?
Yeah, that's something you can do. So what you can do is you can that's sort of what, I mean, that in effect is what it means to evaluate on held out data. So what we've done is that we've taken the probability model and asked it, how probable do you think this sample of held out languages was? So in principle, the higher, it's no different than a language modeling evaluation, right? So a good language model should place high probability on actual sentences, and implicitly it'll take away probability from non-natural sentences, and it should do the same thing. I mean, it's not perfect, but the other thing you can do is you could basically ask a linguist to look at the samples and say, how do you feel about that? And that's something we did a bit of. I mean, they do look relatively natural. It's hard to say. There are some obvious cases that you would not want to see, which is the horizontal vowel system that I showed in the slides is something that never occurs. So if you saw something like that, maybe you had done it poorly.
So the answer, I guess, is you can do this with the linguist, right?
Yeah.
Okay, thanks.
The last slide when you showed I was wondering what the evaluation was.
This? Oh,
yeah, no, this here. Yeah, could you say a bit more about how you did what we're looking at?
Oh yeah, sorry. The paradigm we used was we took a large corpus of languages, probably show this more explicit, And we had a portion for test, a portion for dev, and a portion for, for dev, and a portion train, dev, and test. So we optimized the parameters on the train portion and did our hyperparameter selection on the dev. And what this is this y-axis here is cross entropy and nats of the held out data. So here, these different colors here are effectively a hyperparameter of how many underlying phonemes we believe, and this tells you how well they did. So what we've noticed here is that if you don't believe there are more than, you need at least 25 underlying prototypes for these models to really do well, comparatively, and that you get a little boost from dispersion. That is the move from the Bernoulli point process to determinantal point process. And once you add the nonlinear transformation, you get a very minor boost as well. Nothing to write home about. But the big difference here is the linguist. That's the outlier. So what I'm interested in, and what this shows, is that the representations through the IPA representations that were proposed by linguists aren't very good at predicting vowel, aren't very good. And the reason for that actually has to do with what IPA means. So IPA symbols aren't cross-linguistically compatible. They look like they are, but they're really meant to be interpreted within one language. That is, if I use the symbol I in language X and you use it in language Y, those sounds are similar, but they're not going to be the same sound. There's a lot to say about that. But this basically means that the basic phonological symbolry is not fine-grained enough for this task of predicting held-out vowel systems. And this is something that you'd only discover if you used a machine learning model, right? Because when linguists, if you look at a book on phonological typology and you just compare the different charts, they're not going to look at a level of specificity that this would pop out.
Other questions?
So thanks for the talk. I was wondering, normally the research concerning generating like text from scratch for a particular language has a lot of applications. But I'm just wondering, what is the real life application of generating totally new language? So it's very nice. So we have a totally new language. So what is the real life application of that?
Right. So I mean, I guess I'm not interested in generating new languages per se. I motivate the scientific question of that. So what I want to know is well, here's the real question. I mean, so if you see that chart and you say there are 6 possible word orders, and why is it the case that OVS is so rare? Like, that just is asking for a scientific investigation into that right there. So I want to explain why that's true. Right? It's not enough just to say it happens to be that way, because you wouldn't expect that to be true if every language was sampled without some sort of undergirding principle, right? So it's really a scientific question. And you could say, well, what does it matter? So I would say it's sort of the fundamental question about the brain, really. So there is likely something about the brain that biases us towards preferring these different languages. That's basically the universal grammar assumption, that there's something that's built in, right? So it's sort of a very deep scientific question, I would say. But that's a much harder question to motivate, because I have to explain to people why we should care about those 3 categories in their order. Whereas if I talk to you about generating languages, it's a much more accessible introduction to this topic of typology. But if you're asking, I mean, you could replace David Peterson. That's what you could do with that.
Okay.
Do you have any hyperparameters in your models, for example, in the neural Gaussian model? And if yes, on which data do you tune them? The second question is, again, pretty generic. Do you do any statistical significance tests, especially, for example, in the last results that you showed?
Yes, we do. We tune them on dev data. You could go to the paper for the exact specification. I've tried to present ideas here at a high enough level that you could swap in the number of hidden nodes to your own liking. Of course, that number should be tuned as well as the number of layers on your dev data. But I believe there are significance tests. I have to check the paper. I mean, it would be a permutation test, I guess. I hope I did.
Thanks.
I should have.
So I'm wondering here if there's also kind of like does like geography play a role, or like social aspects, you know, also play a role? Because I'm looking here at the examples that you have, and it seems like Japanese from Latin, they're quite far as like, you know, geographically where they're placed or whatnot. But maybe like there is an influence between, you know, languages for some historic reason, or something happened, or I don't know.
Right, so there's a lot to unpack in that question. So the first thing is genetic factors. So clearly related languages have similar typological properties. Dutch is similar to German due to historical factors, well, specifically genetic factors, and they happen to be geographically located next to each other for the same reason, right? So they're, that's just true. But there's a deeper question there, which is, does geography affect typology? That's a controversial issue. So every once in a while you'll see a Nature article or something, or science article, that'll proclaim that there is some relation between tonal languages and the altitude at which the language is spoken or something. And those claims tend to be contested and based on very small amount of data. But that doesn't necessarily mean they're false. It just means that people disagree about them. So, what was there another part of your question? Was there a link?
I guess the follow-up to that would be like, if there was something like that as a condition, could you try and model that?
Yeah, I mean, so we have, yes, you can. And I mean, but you have to be very careful about what you're modeling, right? You might want a sort of an explanatory theory that explains how altitude affects these things. Oh, sorry, you also asked about societal pressures. So that's a big one. That's also very contested. So you're asking whether society will affect the grammar of your language. I think most people believe that's not true, but there are those that do.
Okay. So I think it's maybe time to thank Ryan again. There is a present.
Thank you.